Here's another first order problem, and this problem is actually similar to the one we did in the previous video, except this one has an inductor, and you can see that the inductor here is connected across a 20k ohm resistor, and we have a 10k up here, and the switch closes at t equal to 0. So just like I said before, when you're doing problems like this, you have to first determine whether the storage element is gaining stored energy over time or whether it's losing stored energy over time. And here it's simple to decide because, or to determine, I mean, because our inductor current is initially 0, so initially there's no stored energy for this inductor. And then at t equal to 0, when the switch closes, that connects this energy source up to the part of the circuit where the inductor is. So it's going to be gaining stored energy as time progresses. So that means that since we have an inductor, it's going to be the current now that increases as this 1 minus a decaying exponential. Okay, remember for inductors it's the current that builds up over time as it gains stored energy, and for a capacitor like the previous problem it's the voltage that builds up. And for an inductor, as we're gaining more stored energy with the current increasing, the voltage across the inductor is going to be decaying exponentially, as you see here. So we're now going to use that three-step approach to find where these two curves start, where they end up, and how long in between. And we're going to start with finding where the curves start with the initial condition, the t equals 0 circuit, t equals 0 plus circuit. Also, even though I'm following the same order as I did in the previous capacitor problem, where I'm first doing the initial condition analysis and then the steady state and then the time constant, you know, these three analyses can be done in any order, so there's no significance to this particular order. They can be done in any order. Alright, so here I replaced the inductor symbol with an open, because as we talked about previously and as on our sheet, if you have an inductor that doesn't have any initial stored energy, well, at t equals 0 plus, it acts like an open, right? It's just the opposite of the capacitor case. So now we just need to solve this circuit, and if we find the current for the open, that's the current for the inductor at t equals 0 plus, and if we find the voltage across the open, that's the voltage across the inductor at t equals 0 plus. Okay, what should be easy is you know, we've seen this many times, that current for an open is 0 by definition. Okay, and then we can find VL at t equals 0 plus just by using voltage divider, right? Because the voltage across this open is the same voltage as what's across the 20k, since the open and the 20k are in parallel. So that's just going to be the 10 volts times 20k over 30k, and that's 6 2/3 volts. Okay, so this analysis yields where these curves start. See this voltage curve, this decaying voltage curve right here. Its initial value at t equals 0 is 6 2/3 volts, and our current here is starting at 0. Alright, so the next step I did was steady state. So at steady state, the inductor is acting like a short circuit, again just the opposite of the capacitor case. So now if I find the voltage for that short, that's the voltage for the inductor at steady state, and if I find the current for the short, that's the current for the inductor at steady state. Alright, so the easy one here is that voltage across the short is 0 volts by definition. And just like we saw in the capacitor problem, we have the same sort of setup here where since you have a short in parallel with the resistor, all the current ideally goes through the short, none goes through this 20K that's across the short. So you're going to get 10 volts divided by 10 kilo ohms, which is just a milliamp. Okay, so these are our steady state values. So these are the values that the curves end up at, you know, after 5 time constants in practice. Okay, you're going to be 0 here, 0 volts, and this final current from the inductor, that's the 1 milliamp. Alright, so the only thing left is how long it takes between t equals 0 and steady state, and that's where the time constant comes in. Okay, now here, one thing to be careful with is that, remember for the capacitor case, the time constant is R times C, and when you have more than one resistor, it's Req times C. Well, a time constant for an RL circuit is, as you see here, it's L over R. Okay, if you just had a single R, it'd just be R. But since we have multiple R's, it's R equivalent. Okay, so inductance divided by resistance is equal to time. And this Req is from the perspective of the inductor. So from the perspective of the inductor, these two resistors are in series, or excuse me, parallel, because once this current here, if you imagine a current flowing, once this current gets inside the circle where the resistors are, there would be more than one path, so they're parallel. So our Req is the 10K in parallel with the 20K. So when you do product over sum, that's going to come out to 6 2/3 K. Alright, so now the tau is 3 millihenries divided by 6 2/3 K ohms. So we got minus 10 to the minus 3 divided by 10 to the plus 3. So when the 10 to the plus 3 comes up top, it's 10 to the minus 6. So you see we're going to get microseconds here. And in fact, it comes out to 0.45 microseconds. And then it's 5 of these. So 5 taus comes out to, let's see, that's going to be 225 microseconds. Yeah, 225 microseconds, right? Let's see. Actually, if we get the calculator here, right, we got 0.45 times 5. Oh, 0.45 times 5. So that's 2.25 microseconds. Okay. It didn't sound right to me there. Good thing we checked. Alright, so 2.25 microseconds. Right, that's 5 times 0.45 microseconds. Yeah. Okay. So that's the amount of time it takes. Okay, going back to our curves here. That's the amount of time from t equals 0 out to steady state. Okay, that's the 5 taus. Okay, for both of these curves. Okay, which again came out to be 2.25 microseconds. Alright, so actually let me clean that up a little bit just so no confusion. Okay, micro. Alright, so this was just another example of a first order circuit type of problem, this one involving an inductor, and we have several more examples coming up in future videos.